Hello community, let's talk about Q-star. It all started 2017 with a cooperation of OpenAI and University of Berkeley Computer Science and Department of Mathematics. So, let's start. At first, of course, what the hell is Q? Now, it is rather easy. Q is a reinforcement learning algorithm designed to identify an optimal action selection policies for a given finite Markov decision process. So, Q-learning is simply one of the algorithms used in reinforcement learning to guide how an agent learns from an interaction in an environment where it can move around and gets feedback. And the Q-function, now this famous Q-function is simply denoted here as a Q, depending on S and A, estimates the expected cumulative reward, also called the utility, obtained by taking an action A for action in a state S for state, and then following an optimal policy thereafter. So the value now of this function at a specific parameter set is a prediction of the total amount of the reward of an agent can expect to accumulate over the future, starting from a state S, taking action A, and then following the best possible strategy. So now you see exactly where Q-learning is located. Now, the learning process itself is rather easy if you look here at a simplified picture. In Q-learning, the agent interacts with the environments and simply updates the Q values based on the rewards it receives, whatever is your agent. Now, the core of the Q-learning is here the Q-learning update rule. We will see this a little bit later on in a little bit better mathematical representation. But you know this here from kindergarten, it's called the Bellman equation. So, S is our current state, A is the action taken, R is the reward received, S slash is here the new state after the action A, Y is here discount factor, and the alpha is the learning rate. You know this. So, very simple way to calculate this. We will do an example in a minute. Policy. Q-learning aims to find a policy that maximizes the total reward. Simple as that. This policy is derived by selecting action based on the highest Q value in each state. And the optimized policy, this is the policy you're looking for. This is pi star. And you might say, hey, pi star, this sounds interesting. Yeah. At a state S is given by the action A that has a maximum Q value for that particular state. Great. Two important things you have to remember. Model-free and off policy. Q-learning is a model-free approach, meaning it doesn't require a model of the environment. This means the transition probabilities and rewards for all the state action pairs, as I just showed you. And off policy, it can learn the optimal policy independently of the agent actions. So the agent's policy can be different from the one it's learning about. This is beautiful. So what is the insight? Q-learning is now a fundamental concept in reinforcement learning, often described as a model-free off-policy algorithm that helps agent learn the value of action in different states without requiring a model of the environment. And this is beautiful, without requiring a model of the environment. This is what we're looking for. Algorithm focus on learning through experience and adapting based on received rewards. Easy as that. For Ben and my younger viewers, what is reinforcement learning? Explanation. What is a policy? And the Q-learning objective. Explained for you of what is a Markov decision process, is a finite Markov decision process, and the outcome depends on the state, and yes. So, summary for the simplest case, what is Q? Q-learning employed within the context of reinforcement learning, systematically evaluate and improve the choices of an agent when an agent is wandering around in a predefined environment and he is learning to perform his task. Focusing on learning which action yield the best long-term results, the optimal policy environments, clear states, clear action, but potentially complex or uncertain outcome and rewards. Learning I just showed you. Beautiful. The simplest example I can think of, an agent is in a grid with 4 states, A, B, C, D. And an agent can choose now. The agent has 2 actions in each state. You can stay or you can move. The simplest chess game you can imagine. And the goal for the agent is to learn to navigate from any state to a particular state, let's call it D, where the agent will receive here the gold medal, a reward for his actions. So this is what he is looking for, this particular agent. The reward structure is simple. Okay, not a gold crown, but moving from D to any state yields a reward of plus 10 points. And moving from any other state yields no reward, 0 points. So, sorry, we're just giving out points here. Now, let's see if we integrate this in our Q-learning procedure. Suppose the agent is in state B, he decides to move and reach a state D. To receive a reward of plus 10 points, we update the Q value for the action move in the state B using our Q-learning formula. You have it. These are the current state, the action taken, the new state, the reward function, the learning rate, the discount factor. And this is it, beautifully. And if you use the formula and you fill in now our particular parameter, you see here we have now a Q value of 5. So you see it is as simple as this. So the Q value of 5 for the action move in the state B indicates that this is the action is expected to lead to a positive reward, moving towards your goal, your cell D. As the agent continues to explore, these Q values will be updated to reflect the optimal action in its state, and the process repeats for various state action pairs as the agent learns here the most rewarding action over time. This is the simplest version that exists. Beautiful. Now, you notice, you have seen this here, the Neural Information Processing System 2023 was a beautiful paper. It has now a reprint and update here, end of October 2023, University of Berkeley and Toyota Research Institute. And now we're talking brand new here for residual Q-learning, online, offline policy customizations. Let's have a look at this now to take a step further. Now at first, we have now to distinguish between imitation learning and reinforcement learning. IL and RL are both used to train agents to perform tasks. Beautiful. But imitation learning is about copying expert behavior. For example, if you have 100 examples or 100,000 examples of mathematical formulas on how to solve equation, this is expert behavior you want to copy. So you use now imitation learning and not reinforcement learning, because reinforcement learning is about learning through the consequences of action in the pursuit of a goal defined by rewards when an agent is moving in its environment. So again, what is the delta between those two? It is important that we make this absolutely clear. Imitation learning relies on expert demonstration, while reinforcement learning relies on feedback from the environment. Reward, penalty. Imitation learning focuses on mimicking observed behavior. How to solve a mathematical equation. What is the exact way? Give me 100 examples. While reinforcement learning focusing on maximizing cumulative rewards, exploration and exploitation. Remember those two words because they will become important when we apply here a Boltzmann equation. Feedback. Imitation learning typically uses here binary feedback based on expert examples. RL uses reward signal. You know all of this. This is just for summarization. Now, policy customization is something new, something nice. So the goal is to customizing here our policy for diverse downstream tasks while retaining their imitative nature. What does it mean? You have a system that learns something and now you have different, diverse, 1, 2, 3, additional downstream tasks that you want that the system has an optimal performance. So you have to customize now the policy for those additional downstream tasks. Therefore, the concept of policy customization in imitation learning, traditional imitation learning involves here learning behavior from demonstration, useful in complex tasks where designing reward function is challenging, or when mimicking expert behavior, mathematical, physics, whatever is desired. However, these imitation policies might be too rigid, only replicate the demonstrated behavior without the flexibility to adapt to varying requirements of different tasks. I can give you here a quadratic equation, I can give you here 100 examples, but maybe on the 101st example, there's now a little difference, so there's a problem. Now, policy customization emerges here as a solution to this limitation. It involves now modifying a pre-trained policy so that it not only retains its original characteristic, but it also meets now additional requirements of our specific downstream task. And I will give you an example of a downstream task in a second. Oh, okay. This new paper, now the update on residual Q-learning here, addresses now exactly the challenges of the policy customization of our system. And they have now a new framework, residual Q-learning. designed to work within the constraints of not having access to the inherent reward or value function of the prior policy. We don't know it. But it formulates a policy customization as a Markov decision process with the reward function combining the original demonstration reward and an additional reward specified by this single or multiple downstream task. And the residual Q-learning framework operates by learning a residual Q function. Yes, you know this. Maximum entropy policy for the targeted MTP. This we will look a little bit closer in 1 minute. Just let it sink in, try to understand it. Practical implementation, develop a family of residual Q-learning algorithms, suitable offline, online policy customization. Yes, beautiful. We just want to understand the basics. Residual Q-learning, you have a basic task. Think you are in a vehicle and you are on a highway. And the basic task is drive the vehicle through the traffic safely and efficiently. Do not crash any other cars, and you have 3 lanes. Beautiful. You have your reinforcement learning and your imitation learning. Great. And then you have, let's say, just one add-on additional task. Stay on the rightmost lane if possible. If you go there to this page, I'll leave you the HTTPS link in the description of this video. You can see this as a video. Maybe it is a little bit better. Otherwise, I just tell you, goal is stay here on the bottom rightmost lane with your car and only overtake here to the 2nd or the 3rd lane whenever it is absolutely necessary, unless you stay at the rightmost lane. So you see, you have now additional policy implementation. And as I showed you in my last video, when we had multiple LoRa adapters on our LLMs or VLMs, here again, we have a very similar approach. You have add-on task and add-on policy layers. And how you do this has been solved here exactly for us. Great. So these algorithms designed to adapt to a prior policy to new tasks by combining the original behavior with additional requirements. And in this study, if you have seen it at a conference, 3 key algorithms were presented for 3 different settings and requirements. At first, we have the residual soft Q-learning. Now I may say, hey, what is the soft Q-learning before we go to the residual? In a minute, give me a second. So this algorithm adapts the soft Q-learning methodology for offline policy customization. Yes, you know this, but our action space is discrete. It is a non-continuous space. This is the most important fact here. Updates parameter, minimizing the temporal difference error. Target residual Q value computed considering the add-on reward function and the prior policy. Beautiful. The task demands discrete action decision. Beautiful. Easiest case. I will show you soft Q-learning in a second. Then we have 2 other cases. This is the so-called residual soft act critic case if we have a continuous action space. A little bit more complicated, we minimize the expected Kullback-Leibler divergence between the current policy and desired maximum entropy policy. I will explain this in a second, Ben. Give me just a second. And then we have something very beautiful, but this I would dive into a little bit of mathematics, residual maximum entropy MCTS. Great. So this is now the end of this simple explanation. Now science start. Up until this moment, we just had Q. Now, Q star. Q star is an old fellow. Q star we know since 2017. If you go back, however, to this equation here, for here reinforcement learning and residual Q-learning here in particular, you see even at the end of October 2023, we have here the term Q star. And this is here a particular soft Q function that satisfies here the soft Bellman equation. And you will say immediately, hey, wait a second, this Bellman equation looks a little bit more complicated than the Bellman equation you showed us here about 5 minutes ago. And yes, of course, this is now science. So if you have a PhD in theoretical physics, this is now the place to learn. Great. Entropy augmented cumulative reward inherent to the demonstration resulting optimal policy follows a Boltzmann distribution. Hello, physics. Yes, you know this. Now you understand this normalization factor. Beautiful. However, Ben, for you, it is Sunday afternoon and I have here my time just trying to make it easy for you to understand this. So I tried here in my simple words that you get an idea. What are we talking about? We are talking here about maximum entropy reinforcement learning, focusing here on policy learning and continuous action spaces with an infinite horizon Markov decision process. But now look, now comes the important part. we deal here with learning policies that not only aim to maximize the reward, but also seek to maximize the entropy, which in this context now implies maintaining stochasticity and unpredictability in the agent actions. So we want here that our agent that interacts here with an environment has here two main functions. And this core idea is balanced here by the exploration through the entropy maximization and the exploitation. So we want to have both maximum entropy maximization and reward maximization. So these are two functions our agent has to be able to fulfill. So the object now is to learn a policy that not only achieves one of them, for example, higher rewards, this is the standard reinforcement learning objectives, but also maintains a high entropy in the policy action distribution. Again, stochasticity and unpredictability in the agent actions. Beautiful. This is expressed as maximizing the sum of the expected rewards and entropy of the policy at each state, weighted by a factor, yes, you know this, which balances the two off, and you can do a little bit of shifting and wiggling around, but this is not the important point. You have to understand it is about agent, and the agent should have exploration and exploitation capabilities. This is why we do this. So, soft value function and the Q-learning approach, we want to go to Q star. The approach involves defining now the soft version of the value function in our Q functions. So, Q-learning, Q function, we know this for quite some time. Now, the soft Q function is defined in a way, incorporates the reward as well as the entropy of the policy, and a soft Bellman equation is used for the iterative updates. This beautiful equation here is now doing here our system updates. Gorgeous. You got it? Beautiful. Let's go on. To see where the Q star term originated, July 2017, we have here OpenAI, writing here with University of Berkeley, Department of Computer Science, and University of Berkeley, Department of Mathematics, and the International Computer Science Institute. They write here about reinforcement learning with deep energy-based policies. And they, OpenAI and Department of Mathematics, UC Berkeley, examine here something very particular. They have here a soft Q star functionality that they examine here in 2017. Can you imagine this? And they go here and they explain to you exactly what they're looking for. And I tried to summarize this in my last slide here in a very simplified way. But this here is, if you have a PhD in physics or mathematics or whatever you have, you get this point. However, they said, hey, this is not that easy. So our theorem 1 or our theorem 2, that the soft Q function satisfies the soft Bellman equation. You see Bellman equation really important here in this thing. And here we have our Q star soft function, where the soft value function V is also given here by equation 5. Here, beautiful, we know this. Theoretical physics, great. However, this is not simple. This is, if you see this, you say, wait a second, show me this. And they have in their publication, OpenAI and UC Berkeley Mathematics, they prove this to you in the Annex 2, the soft Bell equation and the soft value iteration here exactly. So if you want to learn more about the Q star approach, it is in its origin here from 2017, a rather simple approach, Boltzmann equation, theoretical physics, and now they apply this. Now, what is the current OpenAI and board drama with the Q star paper? I don't know the recent Q star paper, how much they could develop this mathematical theorem further, how far they could have this Q star functionality expanded here on GPT-5 maybe. But to give you an idea and an understanding and say, what the hell is Q star? We know Q star is with us for a long time, but maybe not that trivial here for pure coder or for pure programmer. But if you have a PhD in theoretical physics, hey, you are good to go. And this is the end of the video. It is my Sunday. I spent multiple hours here. I hope you find it helpful what I prepared here for you. And it would be great if you would become a subscriber of this channel. See you.